In this video, I'd like to continue talking about trig identities from reflections and rotations by looking at one final example problem that is slightly more challenging since we're dealing with the tangent function. But like the previous problems, we are dealing with the unit circle. And remember, for some coordinate on the unit circle, the x and y value are simply the cosine of the angle theta for the x value, and for the y value, we have the sine of the angle theta, and theta is measured positively from the positive x-axis if we go in the counterclockwise direction. If we go in the clockwise direction, the angle would be measured negatively. Now, for the tangent function, it's important to remember that on the unit circle, the tangent is the ratio of the y value of the coordinate to the x value. Or in other words, it's the sine of the angle divided by the cosine of the angle. But it's important to recognize that it is this ratio here of the coordinate points, since the y value is the sine value and the x value is the cosine value. We took the y value down here and divided it by its x value, 0.1. Now, for this first expression, we need to take our angle theta and add pi radians to it. So if we're at this point on the unit circle and we add pi radians, or 180 degrees, we will end up with a ray on the opposite side of the unit circle, which, if we draw it correctly, will form a straight line with the ray that we already have. Let me redraw that. And at this point over here, we would need to consider the x and y coordinate. Now, the x value, notice, would be the opposite of the x value here. And same for the y value. The y value for this point is down here. The y value at this point is right up here. And if we fill in those coordinate points, the x value would be at minus 0.1. We're on the left half of the coordinate plane where the x values are negative. And the y value will be positive 0.99, since the y values are positive on the upper half of the plane. And when we look at the ratio of the y value and the x value, let's write that in over here. This would be 0.99, the y value or the sine value, divided by the x value, which is minus 0.1. And notice that we effectively have the exact same ratio we had here. The negative is just on the bottom, but overall, this would simplify to minus 9.9. So we have the exact same answer as we did for the tangent of theta when we add pi radians. And we could put minus 9.9 into the box here. In fact, with the tangent function, it's true that whenever you add pi radians, or actually subtract pi radians, either way would work, that this is simply equal to the tangent of the angle. This is an identity we derived in a previous video. And if we look at the graph of the tangent function, it essentially repeats itself every pi radians. And if we look at this second expression, the tangent of 2 pi plus theta, or it might be easier to read it as theta plus 2 pi, either way works, but we're starting with our angle theta down here, and we're adding 2 pi radians, bringing us all the way around the unit circle back to where we started, meaning that the x and y values at tangent of 2 pi plus theta would be the same as the tangent of theta. It is true that when we take our angle theta and we add 2 pi as many times as we'd like, so we can add multiples of 2 pi where k is some integer, it could be negative as well, that this is just equal to the angle theta. And we can say that the tangent of 2 pi plus theta is just equal to the tangent of theta. And since it has the same x and y values, we would have this exact same ratio up here, meaning that the tangent of 2 pi plus theta in this case would just be minus 9.9. And we can also understand this from this identity here, When we add pi to something, it doesn't change the tangent function. So in this case, we're just adding pi twice, but it would still be the exact same function.